Good morning, students. Welcome back to supplementary video lectures. Based on the request from many of the students, uh, here we are going to discuss about the analysis of continuous beams using stiffness method. Earlier videos, if you have seen, we have discussed about the and practice about the solved example of the continuous beam analysis using the slope deflection and moment distribution method. Here, today's session in this video we have to discuss that how that stiffness method is a more convenient and easy to use and user friendly as compared to the earlier methods. So let's start. In between we will discuss about the advantage of the stiffness method, and we will see the difference between the previously methods based on that which we have analyzed the beams. So first we have to start with this word. What is the meaning of the stiffness? So, as we have discussed in the class also, that for any system, when we are applying any kind of the actions, suppose for example here there is a one spring is shown in the figure, and we are applying the force in this direction, so it will be going to deflect, and because of that, this is the deflection delta amount. So the relation of the force and displacement with the stiffness is like this. That is a force equal to stiffness into deflection, or in general, if we called stiffness, that is nothing but it's a ratio of the action by displacement. Action can be anything, and with respect to in the same direction, the displacement of it is called as the stiffness of the member. So stiffness is defined as the action required for the produce the unit displacement. Generally, in the case of the analysis of structure, we are using the action in two way. Either it is a force or moment. Now, for example, if we are considering horizontal force here, so with respect to that horizontal force, whatever displacement in that same direction we have, that is called as a stiffness. So that means here when we are considering the force, so corresponding translation in that direction and ratio of that two, we will consider as a stiffness. Similarly, suppose in any member, if there is a moment is acting, and with respect to it, that moment, the rotation at the same location in the member, the ratio of that moment by rotation is also considered as a stiffness. So only we have to remember this thing that with the corresponding to the action, whatever displacement in that direction and ratio of that action by displacement is considered as a stiffness. Let me start with the practice example. This is the same data which we have used earlier in the case of the slope deflection and moment distribution method. So you can compare the entire method. It is a just a modified version, advanced version of the slope deflection method, in which we are using the equations. In place of that, here we have to use the matrix, because this method is a user friendly, because we can make computer program easily in the simple statistical tools. Also you can use the analysis of the any kind of the beam which is dependent on the nothing but KIs. So this is a displacement method, and it is an advanced version of the slope deflection method. So here, as two span continuous beam is given, and we have to analyze this beam using the stiffness method. So what is the first step? Like we are using in the slope deflection method, here also we have to find out first Ki of the beam. So you can see over here, if we are neglecting the axial deformation, here it will be 2 Ki, which is a nothing but it's a rotation at B and rotation at C. Now, in the second thing, that we have to show the displacement by restraining the structure. Restraining the structure means all we will consider as a fixed support, and unknown displacement which we have considered in the Ki, theta B and theta C, that we will going to represent like this as a terms of the D1 and D2. Here we are assuming the rotations in the clockwise direction. So with respect to it, whatever action we will consider in the further up to the end of the this example, we have to consider everywhere this assumption as a clockwise. If you wish, you can assume as a anti-clockwise direction also. Then we have to consider the anti-clockwise as a positive in that case. So here we are assuming the that our unknown displacement, unknown rotations at B and C are nothing but it's a clockwise, and that we are representing as a T1 and T2. Second step, that is a AD vector. Now, what is the AD? AD is a nothing but action in the actual structure corresponding to unknown joint displacement with respect to free degree of freedom. So here AD1 is a 0, AD2 is a 0. How? As you can compare with the previous figure, that D1 and D2, with respect to the D1 and D2, in actual structure, is there any joint load or joint moment is acting over here at the B? Is there any moment is given? No. So that's why AD is a 0. With respect to rotation at C, is there any moment is given in the actual structure? So that is also no joint moment in the B and C. So we will consider AD as a 0 0. If with respect to the degree of freedom, if any joint moment, or with respect to the if the vertical displacement is unknown, so with respect to that, if there is a vertical joint load is acting on the joint, then we have to consider the AD. So in this case AD will be 0. Second, ADL is a nothing but action in the restraint structure corresponding to the unknown joint displacement due to the load with respect to the degree of freedom. So here this is one beam, and we have to find out the friction moments. As here 50 kilonewton is acting, so earlier also we are convenient to use the friction moments here. So that is a WL by, yeah, WAB square by L square, while on the right hand side it's a WA square B by L square. Left anti-clockwise, right clockwise moment we have to consider for the friction moment. Similarly, second span BC, for that we have a moment that is a WL square by del, and the direction is the same, anti-clockwise and clockwise. Now we have to consider the ADL1. What is the meaning of the ADL1? With respect to unknown degree of freedom, we have to consider the total action in this figure. So for example, if we have a consider first one, so D1, that is our rotation at B. With respect to rotation at B, what is the moment at B we can see in this figure? So that is a this one, that 36 clockwise and 62.5 anti-clockwise. The total moment is a 36 minus 62.5. Similarly, rotation at C. So with respect to it, we have to see moment at C as a ADL2. So ADL2 is nothing but 62.5 clockwise. So our ADL vector is like this, minus 26.5 and 62.5. So first, in AD, we have to just consider joint loads, while in the ADL, we have to consider member load. There is a difference between these two vectors. Third step, that is the stiffness matrix. We have done lots of practice, but you can take a reference of this example, and again you can, if you have any doubt, you can revise it. So simply what we can say as a stiffness matrix coefficients, it is a Sij, which is nothing but action at I due to unit displacement at J. That if you are giving the unit displacement at one point, and whatever same point if action will be there, that is nothing but action by displacement, which we are defining as a stiffness, as we have discussed in the beginning of this session. So with respect to the corresponding displacement, we have to consider the action. For example, over here we have a D1 and D2 is a nothing but it's a rotation at the respective point. So we have to consider the moment at this point B and C with respect to the unknown degree of freedoms. Next point, we have to apply one by one displacement as Sij, where J is a nothing but it's a unit displacement. So we have to one by one apply the unit displacement over here, D1 equal to 1, and similarly afterwards we'll give the D2 equal to 1. Now what is the exactly D1? That is a rotation at B. So we'll rotate this joint B, and because of it, what is the moment in the both the span? As B joint is a rotating, so both the span will be going to affect. So in the near end, it will be moment is a 4 ei theta by L, while in the far end, that will be 2 ei theta by L. So here respective L we have to put, as well as the change of the moment of inertia also we have to consider. Here it is a change of moment of inertia is a 2y, so we have to consider over here. So here first thing, that action at B, right? So action at B is a nothing but it's a total summation of the moment at B due to unit displacement at the B. So that is a nothing but it's a S11 4e2i by 5 plus 4ei by 5. So there is a nothing but 2.5 2.4 ei. Second, action at C, right? Because our second point of unknown degree of freedom, that is a C, so we will consider S21. Action at point number 2 due to unit displacement at the point number 1, so that is a 2 EI by 5, as total moment over here is a 2ei by 5. All the moment are clockwise, so we will consider just addition of the moments. So that is our first column of the matrix due to the first figure, that is a 2.4 and 0.4. Same procedure we have to repeat, and we have to do for d2 equal to 1, which is our second column. So d2 equal to 1, if we apply, so joint C will be going to rotate. So the moment at C will be 4ei by L, while moment at B will be 2ei by L. Now whatever moment at B, that will be considered as a 1 2. So that is a 2ei by 5, and S22, that will be 4ei by 5. That is a moment at C. So that is a that is our stiffness matrix: 2.4, 0.4, 0.4, and 0.8. Next, we are taking common EI. So this is our final stiffness matrix. Based on this AD, ADL, and stiffness matrix, we have to calculate our primary unknown, as it is a displacement method. So our primary unknown is nothing but it's a displacements, which is our unknown d1 and d2, or rotation at B and rotation at C. So this is the equation, as we have discussed, that stiffness into the displacement, that is equal to action. So stiffness, if we take on this side, so it will be become a inverse, as it is a matrix. So D equal to S inverse AD minus ADL vector. So S inverse, when we are finding, so this is a stiffness matrix. We have to find out the stiffness matrix inverse. So whenever it's a 2 by 2 matrix, just we have to do the cross multiplication. We have to find out the determinant: 2.4 into 0.8 minus 0.4 into 0.4. So it is a, we have to just multiply the principal diagonal here with the 2.4 into 0.8 minus 0.4 into 0.4. So that will be give the answer as a 1.76. Next, we have to change the position to find out the adjoint of the matrix. So principal diagonal value will be going to interchange. Okay, so here principal diagonal value, if you consider 2.4 and 0.8, that position is going to interchange. And while remaining two, that is a zero point 0.4 and zero point 0.4, that is a become a negative. So that is a become a our stiffness matrix. Second point, that is a nothing but it's a second point, that is a our AD minus ADL, and we have to find out the displacement based on this. So if you are considering AD, that is a 0, ADL, that is a minus 26 and 62.5 from the previous step. So what is the next? That is a, we have to just consider the reverse sign over here. We have to deduct these column vectors. So 26.5 and minus 62.5. Here we have a 2 by 2 matrix and 2 by 1 matrix that we are going to multiply first row into the first column of the matrix, and that will be going to divide with a 1.76. So the answer will be 1 by EI 26.25 and minus 91.25. What is the meaning of this plus and minus sign? As we have assumed both the displacement as a uh, clockwise initially. So here first one, there is a 26.25 is a clockwise, but second one minus 91.25, which is a anti-clockwise direction. So that is the first primary unknown displacement from the initial steps. Now second thing, we have to calculate the secondary unknown, that is our member and actions. So here there are three member and action we have to consider: AM, AML, and AMD. AML means there is a member and action in the actual structure. So there is a nothing but, so we will consider four moment: AM1, AM2, AM3, and AM4. AML, that is a moment action due to the loads, so which we have considered in the earlier for the ADL, same figure we have to use it. That is a fixed moment one. And AMD, that is a moment action in the restraint structure due to the unit displacement. So in that also we have to use the same figure, right? That is a we have used for the deriving the stiffness matrix. Next, so this is our equation: AM equal to AML plus AMD into D. Now, D we already calculated, so that we will put it over here 1 by EI 26.25 and minus 91.25. First, we have to talk about the AML. So, as if you consider the previous step, so here all the am we have considered in the clockwise direction, so we'll consider all the aml and amd actions all clockwise direction as a positive. So this was the first figure which we have considered for the fixed moment. So one by one in the sequence we have to consider all the clockwise moment as a plus and anti-clockwise as a minus. The first one is a 24 is anti-clockwise, so minus 24. Second 36, third minus 62.5 and 62.5. Similarly, we have to consider the another two figure which we have considered to derive the stiffness matrix d1 equal to 1 and d2 equal to 1. So from the first figure, we will write the first column 4ei by L, 4 8ei by L, that is a 1.6, 4ei by 5, that is a 0.8, and 2ei by L, that is a 0.4. Same way, if we consider the second figure, first moment at A is a 0, moment at BA there is a 0, 2 by 5 that is a 0.4, and 4 by 5 that is a 0.8. So we got all the moments over here, and we have to just multiply the amd into d matrix, so it will be like this. Similarly, for row wise you can calculate 0.8 into 26.5 plus 0 into minus 91.25. And once we get these two column vectors, so we have to do the addition of that. So that will be give you our final answer minus 378 minus 78 and 0. Based on these moments, we have to draw the diagram. So as first one is a minus 3, which will be indicate the anti-clockwise moment. Second plus 78, that is a clockwise moment. Minus 78, that is an anti-clockwise moment. And 0, that is a moment at as end support is a hinge or roller, so moment will be 0. So based on the answer, automatically you can verify your answers also. So here we will draw the diagram. As in this all the moments are hogging, we have to just show the like this, we have to connect it, which is showing the support moment, and over that we have to draw the span moment, that is a positive wab by l on this span, and wl square by 8 on the span bc, which is a nothing but positive moment. So that is a nothing but it's a overall view on the stiffness method using the two span continuous beam. Now, before going to end, we will just take a one review that how you can consider the effect of the overhang portion or change in a geometry using the stiffness method. Although we have already considered the change on geometry in this example, that variation of the moment of inertia we have considered, but when we are considering specifically fixed end, right, without considering the support, if specifically one member is changing the moment of inertia, so how we can consider that particular joint, that you have to think. And similarly, if it is a continuous beam with some overhang portion, so that overhang portion, what is the effect of it, and how to at which location we have to consider that one, that you should think about it, and you can write your answer in the comment section. So you should also review the entire method. You can calculate and compare the answer with the slope deflection and moment distribution method, and give your answer that which one you feel as a most suitable or easiest method based on your perspective and why. So with this, we are going to end this session. Always your comments, your doubts will be welcome, and you should share your doubts personally or in the comment section. Thank you so much.